Screen. Share screen, iPhone, iPad, by AirPlay, share. All right. And let's get this centered here, enlarged. Let's get locked in screen. Good. I think that looks like a good image there. Yeah, so I've summarized a bunch of this stuff. There's a lot of fairly complicated formulas to proceed with this. This is the results that we got on making the first pass at quantizing the electromagnetic field, looking at the free field only. So first of all, in the case of box normalization, we define a mode to be a combination of a wave vector and a polarization index. The wave vector has to lie in the lattice and K space because we're doing it in a box. The polarization index just labels the two polarization vectors. You can call them 1 and 2 if you want. Although for the helicity polarization vectors, we label them +1 and -1. They correspond to right and left circular polarized light. Commutation relations amongst the creation and annihilation operators is that all these operators commute with each other unless the two modes are the same. And then in that case, an A and an A dagger don't commute, but give you a value of 1. Otherwise, all commutators are 0. That's the meaning of this. And then we develop expressions for the three quantum fields that we're mainly interested in: the vector potential, the transverse electric field, and the magnetic field. We're just doing this for the free field at this point. So the transverse electric field, in fact, is a total electric field. But in the case of all three of these fields, we have an expansion, as you can see, that gives in effect the Fourier coefficients of linear combinations of creation and annihilation operators with explicit formulas here. We also took the limit in which the volume goes to infinity. In that case, you need to scale the creation and annihilation operators by volume-dependent factors and stuff to make them have a finite limit as the volume goes to infinity. And we obtain these new operators, which I denote by A mu of K. The notation is supposed to remind us that K is now a continuous variable. And these have commutation relations that are like the earlier ones, except the K variable now being continuous gives us a Dirac delta function. The polarizations are still discrete, so it's still a Kronecker delta. Anyway, these are the basic commutation relations. And then writing out the three fields, in that limit where the volume goes to infinity, we now have, instead of a sum over modes lambda, we've got an integral, really a Fourier transform over K space, and a sum on mu is written out explicitly here like this. And otherwise, the structure of the formulas is rather similar. The volume factor has disappeared here from the free factor, from the prefactor. A useful identity we worked out last time is that the vacuum expectation value of a product of an annihilation times a creation operator with different modes, an unprimed mode and a prime mode, gives you this Kronecker delta in the polarizations and a Dirac delta in the wave vectors. This is an easy identity to derive, and it's also, we'll end up using it several times tonight. So that's kind of a review of some of the things we did last time that we're going to need tonight. Are there any questions about this before I go on? If not, then I'll launch on the beginning of new material tonight. So I want to talk tonight about something I can describe by saying we're going to talk about the wave function of the photon. The idea is this: is that we have a new formalism, at least new for this course, for describing the quantum mechanics of particles, and it's based on occupation number eigenbases and creation and annihilation operators of harmonic oscillators and so on. And the point is that it doesn't look anything like the formalism that we've used so far for describing the quantum mechanics of particles, which of course is wave functions. If the wave function is spin, it's a multi-component wave function. So this is the story that we know about from last semester, et cetera, and your introductory courses. All right, so the question then is, what's the relationship between the new formalism and the old one? And that's what I'd like to begin with describing tonight. And part of the result of that will be kind of an explanation of, what do we mean by the wave function of the photon? So it goes like this. Allow me to write script E sub EM for the state space for the electromagnetic field. And I want to use the right pen here. This space is called a Fock space, as in contrast to a Hilbert space. I'm not going to go into the meaning of that exactly, except to say that in field theory, the state spaces we deal with are called Fock spaces. But in any case, this is the space, and we have various operators that act on this space that we've worked out. For example, the creation and annihilation operators do. The field operators, which are linear combinations of the creation and annihilation operators, also act in this space. The Hamiltonian does. The momentum and angular momentum operators, which we talked about, also act in this space. So we have a collection of operators that are physically significant and act in that space. Now let's talk about states that have no photons. So say states with 0 photons in this state space, E sub EM. In fact, there's only one such state. It's the vacuum state 0. It spans a one-dimensional subspace of the state space of the system, and I'll call that E sub 0 here. It's just complex multiples of the vacuum. Now, how about states with 1 photon? Let's look at those next. Allow me to denote a general such state by capital psi sub 1, where the 1 means 1 photon. And to create a single photon state, and I'll leave some space here, we can take the vacuum and we can apply a creation operator, A dagger sub mu of k, like that, and that'll create a single photon in the, from the vacuum. However, this is not the most general single photon state. This is a state that's parameterized by the polarization in K, which now is continuous, runs over all of K space. So there's lots of different states like this. And the most general single photon state then is going to be a linear combination of states like this. So to create such a linear combination, let me multiply by a complex, basically a set of coefficients. I'll call them F. It has to depend on mu and K. I'll call it F sub mu of K, like this. And we'll sum on mu and we'll integrate over K. And in so doing, what we end up with is the most general linear combination of these states that can be created. So therefore, it becomes the most general single photon state. Now, these states fill up a subspace of the state space of the electromagnetic field, which I'll call E sub 1, meaning these are the states that have a single photon in them. Likewise, we can have 2 photon states. Let me call it capital psi sub 2. The most general 2 photon state looks like this. It's an integral over k and k prime. And we have a sum over polarizations mu and mu prime. Let me hold this paper down so it doesn't wiggle. And then we have expansion coefficients, which depend on mu and mu prime and on k and k prime. I'll call that F, like this. And then we have a creation operator, A dagger sub mu of k, and another creation operator, A dagger sub mu prime of k prime, acting on the vacuum. What these 2 creation operators do is they take the vacuum and create 2 photons. The primed and unprimed modes that you see here could either be different or they could be the same. It won't matter. The point is we create 2 photons out of the vacuum, and then we form arbitrary linear combinations of those states with these coefficients F, sum them up to get the linear combination, and this gives us the most general 2 photon state. All right. Now then, this shows, and let's let this set of states psi 2 constructed in this way. Let's call it E sub 2. That gives us another subspace of the state space of the electromagnetic field. And you can see that E sub electromagnetic is decomposing into a set of orthogonal subspaces, E1, E2, E3, E0, 1, 2, and so on, like this, going on out. And this is then a useful decomposition of the state space of the electromagnetic field, basically counting the number of photons in the given states. These states keep getting bigger and bigger the larger the number of photons. This psi 1 formula, one of the things that it does is it takes the states that are in E1 and it associates them with functions F sub mu of k. And so it's a good guess, a logical guess, as a matter of fact, that these single photon states being associated with these functions, that we should interpret that function f mu of k as in effect the quote unquote the wave function of the photon. And this turns out to be correct, or it's a legitimate and reasonable interpretation. So let's do that. In order to understand that interpretation, let me make a few comments. So first of all, here's the formula. Psi1 is expressed in terms of f this way. You can invert this equation to solve for f in terms of psi1, and here's the formula for it. F mu of k is equal to the matrix solvent with the vacuum on the left, and then I have a mu of k, an annihilation operator, and then I have psi1 like this. So if psi1 has this form, you can easily show that this matrix element gives you the wave function. So this is a way of going back and forth between these single photon states and the corresponding wave function. All right. So let's to understand these wave functions a little better, let's compute the norm of our state psi1 scalar product with itself. In order to do that, I'll take this formula for psi1, and in your imagination, I'll write it down a second time. And then for the second one, I'll take the Hermitian conjugate of both sides to convert it into a bra here, and bra's on the right-hand side. And then I have to take the dummy variables of summation, k and mu, and turn them into prime versions in one of the two copies. And then I'll take the scalar product. And if you follow that, then it's fairly easy to write out what the scalar product is going to be. It'll be a double integral d cubed k prime. There'll be a double sum on polarizations mu prime. There's a vacuum bra here. Oh, excuse me, before I get into that, there's the wave function f mu of k complex conjugate times f mu prime of k prime with no complex conjugate. And then that is multiplied by a vacuum expectation value of 0 on the left, vacuum on the left, no dagger, a mu of k in the middle, and then a dagger mu prime of k prime. And then this is running off the screen here. And then I have the vacuum on the right. And what you see is that this is the same thing that our useful identity referred to. This gives us Kronecker delta mu prime, Dirac delta function k minus k prime. And so that allows us to get rid of one of the k integrals and one of the mu sums. This should be mu prime there, one of the mu sums by incorporating the delta functions. And if you do, you end up with a single k integral d cubed k and a single sum on mu. And then you have the absolute value of f mu of k squared. So this gives us the expression for the scalar product. And oops, I ran off the screen again that way. This gives us an expression for the scalar product in the state space, in the Fock space of the electromagnetic field, in terms of the corresponding wave function. Now, for single particle states. This should remind you of what happens in ordinary particle mechanics. If we have a wave function with a particle with spin, we have a wave function we can write as psi m of x like this, which can also be seen as a scalar product of xm with the state psi, like so. And the m value here runs from minus s up to plus s, like so. And then if we do this, then this is all stuff from last semester, then the scalar product of psi with itself can be written this way as an integral over x, d cubed x, and then a sum on m, which runs from minus s up to plus s. And then we have the absolute value of psi m of x squared, like so. So if you compare this, with what we just done with photons, you can see that the f, which is supposed to be the wave function of the photon, is kind of like the wave function of a particle, in which the mu subscript is probably some kind of magnetic quantum number. Now this is in k space rather than in real space x, the scalar product that we're taking. And so it suggests that this is a momentum, that this f mu of k is a momentum space wave function. K space and momentum space are almost the same. So it's a momentum space wave function with some kind of spin index. Now, I think I mentioned this earlier. If we use a helicity basis, which I think I want to do, then the mu takes in the value plus or minus 1. So there's two components here. That doesn't run from minus s up to plus s like we see for ordinary material particles, and that requires some explanation. It runs only 2 values, not 3. That doesn't mean that the photon is a spin-a-half particle. Spin-a-half particle has only 2 components, right? And a photon also only has 2 components, but a photon, it turns out, has spin 1, not spin-a-half. But there has to be a further explanation for why there's only 2 components, and I'll get to that in a minute, at least briefly. But in any case, we can interpret this as the wave function of the photon. Before I proceed with this, let me make some remarks about the 2-photon wave function. Here it is. Here's the general formula for a general 2-photon state. Let's notice the important fact that all creation operators commute with all other creation operators. So I can swap these two if I want. And if I do, it amounts to a swapping of, well, if I do it, it just moves the one with the primed indices, and it just exchanges the two, one with the primed indices and one without them. But these are just dummy variables of summation. So if I then swap them again, by changing the variables of summation, the effect is to take these A's and A daggers back to where they were, but to swap the indices on the F function. So what this leads you to conclude is that this F function might as well be symmetric under exchange of its labels, K mu and K prime mu prime, because the antisymmetric part doesn't contribute to the final state anyway. So we can say then that the 2-photon wave function is symmetric under the exchange of its labels. Well, that's an important point because it leads to the conclusion that photons are bosons. And so let me just put this here somewhere. We got bosons. We're finding that photons are bosons. It emerges from the trend of the formalism that we're using, where we apply Dirac quantization to the classical electromagnetic field, and we end up with bosons. All right. Bosons, of course, are consistent with the usual rules if the photon is interpreted as having a spin 1, which in fact it is spin 1. All right. Now, in the case of these material particles, this XM basis that we're using here, we sometimes call that the representation, corresponds to a complete set of commuting observables that we use for the basis states. I mean, remember, a wave function is nothing but the expansion coefficients of the state with respect to some basis. And the basis is related to some complete set. So in this case, the complete set is the position operator X. I could put a hat on it if you want. And S sub Z for the spin, the M is a magnetic quantum number of that. These are commuting operators. There's 4 of them, of course, 3 components of X. And so this is a CSCO, which is commonly used in describing wave functions for material particles. What about the photon? We've got this mu and K business here. So if I were to write F mu of K in an analogous notation is something like this, is K mu, and then an F like this. Suppose I try to write it that way for the single particle wave function. Then the question is, what is the complete set of commuting observables here? Well, the first one is K itself, which is the momentum. And the second one is an operator I'll call capital omega, which is called the helicity operator. The helicity operator is, can I spell it right? Let me spell it right. Helicity. And I'll say what that is in a minute, but the helicity operator, I'll tell you what it is now. The helicity operator is the component of the spin along the direction of propagation. It's K hat dotted into S. This can also be written as K hat dotted into J, where J is the total angular momentum of the single particle state. Now, the spin operator, if it's projected on any direction whatsoever, it doesn't have to be the Z direction. If you project it in any direction whatsoever, then its eigenvalues always run from minus S up to plus S. So in the case of the photon, since mu takes the values plus or minus 1, it would look like the spin, that these are magnetic quantum numbers that ought to run from minus 1 up to plus 1, including the 0. But actually, in the case of the photon, the 0 is not present. The 0 would be longitudinal polarizations if they existed for a photon, but they don't. So the photon only has the stretch states in which the component of spin along the direction of propagation takes on either its maximum value plus 1 or the minimum value minus 1, but not the value 0. The reason the value 0 is excluded is because the photon is a massless particle. You can understand this at least roughly on the basis of Lorentz transformations. If you have a particle with mass and it has any spin state, let's say in the direction of motion, s equals +1, for example, you can do a Lorentz transformation into the rest frame of the particle. And then once you're there, you can apply a spatial rotation to rotate the spin in any direction you want. You can rotate it sideways if you want, and then you can boost it back again. So in other words, you can create all three spin states in the direction of the particle, if in the direction of motion, if the particle is massive. But if the particle is massless, it doesn't have a rest frame. So there's no option of doing that. And this is a fact that's related to the fact that the photon doesn't have the m equals 0 polarization state. Those, of course, the zero states, of course, would have been the longitudinal polarizations. And we know that photons don't have those. By the way, there's an interesting question about what would happen if a photon had a small but non-zero mass. Okay, so I'll tell you a little about that. So a bit of a tangent here tonight. The question of the mass of the photon is an experimental matter. I mean, someday somebody might determine that the photon has a finite mass. If they do, the theorists are going to have to get busy, because it actually kind of messes up the theories and is not so attractive if that were true. But in any case, who knows? It might happen someday. In any case, experimentalists certainly have tried to make estimates of at least upper bounds on the mass of the photon. And those upper bounds are really very small. I forget the exact numbers, a 10 to the minus 18 electron volts or something. It's less than that. It depends on which criterion you're using for it. In any case, yet still the question remains open. What would happen if the photon really did have a small but non-zero finite mass? Well, one thing that you can tell your children that are asking you about relativity theory is it would mean that light no longer travels at the speed of light, but rather slower than the speed of light. It doesn't make any sense, but you know what I mean. Okay, that would be one effect. Another effect would be that you would have longitudinal photons, which, if the mass of the photon were small, would be therefore only very weakly coupled to the transverse world of electromagnetism that we know since Maxwell. In other words, they would be something like neutrinos in the sense that they don't interact with things very much, maybe even less than neutrinos. On the other hand, there might be a lot of them out there, and maybe they contribute to dark energy, dark matter. Dark matter. Maybe they contribute to dark matter. There's questions about that. In any case, for cosmological reasons, people have been reconsidering longitudinal photons lately. There's a more interest in this topic now, in recent years, than there has been in time before that. In any case, we normally say longitudinal photons don't exist. All right. In any case, there's a good deal more that I can say about this, about the wave function of the photon, and what's going on inside this state E1, the subspace E1 of the electromagnetic Hilbert space or Fock space, and how this is reflected in the wave functions of the photons. But I think I'd better, for lack of time, not go into it any more deeply. Let me just say that it's an important topic if you want to understand the angular momentum of the photon, which is a very intriguing subject, and it's complicated enough that I basically don't have time to go into it in this course. So I'm going to skip it, except just to say that it turns out that the photon is a spin 1 particle in which only the stretched polarizations, the stretched helicity states are allowed, not the transverse helicity states. All right. Okay. Now, I think that's all I want to say about the formalism that we've developed for the free electromagnetic field. So if there's, let me pause here to see if there's any questions before we move on to applications of all this. Any questions?
So when we went from box normalization to sort of like, we got rid of that, like we kind of just went from a bunch of like, I'm just trying to understand how the Fock space sort of emerges from the Hilbert space that we had before.
Well,
when we do box normalization.
as you let the volume of the box go to infinity, the density of states in K space also goes to infinity. So you end up getting a continuum in K space.
Right. So instead of like a list of numbers for every E0, E1, E2, we just have a F mu K, F mu mu prime, K prime, etc.
That's right. But the A lambda and
Okay.
A lambda daggers, which created, or destroyed photons in a single mode in a box, by themselves, they lose meaning when you let the volume go to infinity. And you can see why.
Right.
It's because if I create one photon in a box and then let the volume go to infinity, the energy density goes to 0. So, and the wave function does too. So it's like, it's a singular kind of a state. It just goes to 0.
Right.
What
Okay.
we do is we scale the creation annihilation operator by a factor that involves the square root of the volume, and that saves the normalization. Excuse me, that saves the what it gives us a quote unquote state, which is not really a quantum state. But it's very similar to what you have in ordinary particle wave functions when you want to talk about a momentum eigenstate, plane wave. Plane wave fills up all of space. Its norm is infinite. It's not physical, but it's what you have to talk about if you want to talk about momentum eigenstates. And that's what happens in the case of the electromagnetic field. This creation operator A mu of K dagger applied to the vacuum, such as you see like right here, for this psi1 state. This by itself is not normalizable. This is one reason why I have to multiply by this F and sum and integrate. I create an effect. You can call it a wave packet if you want, but it's something you can use to create normalizable states. That shows here by this normalization calculation, which converts it into the square of the wave function. Obviously choosing F so that it's normalized in this sense gives us a psi1, which is then a normalized single photon state. One might say that these new creation operators in the continuum don't have meaning by themselves, but rather only under an integral sign. You could say the same thing about plane waves for ordinary quantum mechanics. They're not physical states. They really only have meaning when you form linear combinations under integral signs in effect to make wave packets. Then they become something physically you can work with. We use them anyway because they're so mathematically convenient. And this is a similar situation. All right. In fact, it's really very, very analogous to what we do with plane waves and ordinary particle quantum mechanics. All right. If there's no further questions about that, then I want to move on to a new topic, which is applications of this formalism. To do applications, we want to incorporate the interaction of the electromagnetic field with matter. Let me remind you that in our work on the classical electromagnetic field, we worked out the classical Hamiltonian for non-relativistic matter in a certain model. Interacting involved point charges and the neglect of the infinite self energy of the point particles in a given Lorentz frame. We use that model to come up with a Hamiltonian for the interacting matter field system. And if you're doing this week's homework problem, you've become very familiar with that. So anyway, here's what the Hamiltonian is. It's Hamiltonian is the sum over the particles alpha, 1 over twice the mass is m alpha. Then you get a momentum P alpha for particle alpha minus Q alpha over C times the vector potential. It's evaluated at the particle position R alpha, that's squared. There is then the transverse, then there's then the potential, which is the non-retarded Coulomb potential. It's the sum on alpha less than beta of Q alpha Q beta divided by the Coulomb denominator, R alpha minus R beta. And then we have finally the electromagnetic field part, which is the sum on modes lambda of h bar omega lambda, a lambda star, a lambda. This is classical, so I'm using normal variables a star and a instead of a and a dagger. Anyway, that's the Hamiltonian we worked out. It's classical Hamiltonian. This vector potential, by the way, I've indicated it's evaluated at the particle position, but it also depends on the field operators, field variables too, which are classically, these are the a lambdas and a lambda stars, the normal variables. So to be more explicit about what this depends on, it depends on both the particle and the field variables. And this is what provides the coupling between the matter and the field. Now then, if we wanted to deal with the quantum mechanics of the interaction of matter with radiation, it would be logical to quantize this Hamiltonian, to reinterpret the Q's and the P's as operators. This Hamiltonian, you see, depends on the particle positions, the particle momenta, and then the field Q's, Q lambdas and P lambdas, which we denote by capital Q and P lambda, or if you want to, you can replace those by A's and A stars and normal variables. Depends on this collection of variables. That's the classical Hamiltonian. But we reinterpret them as operators, and then it becomes a quantum Hamiltonian. So it's a guess that this is a quantum Hamiltonian that will describe the quantum mechanics of the interaction of matter with radiation. And this is just what we're going to do. So what that means is that, for example, in the case of the free field Hamiltonian, the A star should be replaced by, basically, we're just going to run through and replace the P's and the Q's by the usual, P's and R's, P alpha and R alpha by the usual operators for particles, and then the Q's and the P's by operators with the usual commutation relations, which is equivalent to replacing A's and A stars by A's and A daggers. So let me just erase the star here, exit out, and replace it by a dagger in those two spots. This is already normal ordered, you see, because the daggers are to the left. So that takes care of our 0-point energy there. One further thing we ought to do if we're going to talk about the quantum problem is we ought to include the interaction of the spin with the magnetic field. So for that, I'm going to put inners with a minus sign. It's a sum over particles alpha, the magnetic moment operator for the given particle mu alpha dotted into the magnetic field, which is evaluated at the particle position R alpha. So this Hamilton is now a quantum Hamiltonian. If I took this first term here, which is obviously kinetic energy, and then the potential energy, and then the mu dot B terms like that, that would be the same as the kinds of Hamiltonians we dealt with a lot last semester in particle mechanics, except for the fact that in last semester, the vector potential and the scalar potential were C number fields, possibly with a time dependence. Well, the scalar potential still is a C number field, or more exactly, it's an operator that depends on the particle coordinates only. But the vector potential depends on not only the particle coordinates, but also the field dynamical variables. And that's what couples things together. That's the new element here, in addition to the fact that there's the free particle field Hamiltonian has been added to this. And so it's this term you see, this A, which is going to be responsible for and also the spin term here, which will be responsible for the interaction between the matter and the radiation, the emission and absorption of radiation. Now this Hamiltonian applies for almost any, it's in Coulomb gauge, it applies for almost any non-relativistic system if you follow the model we used. Including atoms, molecules, nuclei, nanotubes, condensed matter problems, and so on. But to make life simple for us, I want to restrict this to the case of a single electron atom. You can think of hydrogen if you want. And if we do this in the Hamiltonian we now just have a single particle now, not just a sum. The single particle is the electron. So the Hamiltonian is 1/2m for the kinetic energy is 1/2m. The electron momentum P plus E over C, the vector potential A, to evaluate at the electron position, which is denoted R here squared. The potential I'll just call V of R. Then we have minus the magnetic moment dotted into the magnetic field B, which is a function of the electron position R. And then we've got the free field Hamiltonian H bar omega lambda times A lambda dagger A lambda, like so. So this is the Hamiltonian we'll use for studying the interaction of the electromagnetic field with our single electron atom. This, by the way, is not in fact a special case of the earlier Hamiltonian I wrote down, but there's an approximation that was involved in deriving it. So let me just mention how that works. If I took the earlier Hamiltonian here and I had two particles, let's say a nucleus and an electron, and put that in here, and then I made the approximation that the nucleus was very heavy, then in effect it turns into a one particle problem, which is the electron orbiting the nucleus, and that's how you get this Hamiltonian out. If the nucleus is very heavy, then it doesn't move. I mean, if it's so heavy it's like in an inertial frame, doesn't move at all, then that means that it's stationary. And that means that the non-retarded Coulomb potential is the correct scalar potential, because there's no retardation. I mean, there's the location of the nucleus at the retarded time is the same as the location at the actual time. So this is the correct scalar potential. And there's no vector potential produced by it because it doesn't have any motion. Its velocity is 0. So that's the physical idea lying behind transforming from this Hamiltonian down to this one. All right. In any case, let's play games with this Hamiltonian. Let's break it up into three terms, H0 plus H1 plus H2. And for H0, we'll take that to be P squared over 2m, the first term from the kinetic energy, plus the V of R. And we'll add the free field electromagnetic Hamiltonian onto it as well, sum on lambda, H bar omega lambda, A lambda dagger A lambda, like so. For H1, we'll take the terms that are linear in the field, or fields, because there's a vector potential there and a magnetic field there. For the vector potential, it's the cross term here. So that becomes E over mc, and that gets multiplied times P dotted into the vector potential A. And if you take this mu here, which is an electron magnetic moment, and write it as minus GE times EH bar over 2mc times the spin divided by H bar, and if we assume that GE is equal to 2, which it is to a good approximation, that cancels the 2 in the denominator, and the H bars cancel as well, then the second term turns into an E over mc times the spin dotted into the magnetic field. And so that's our H1. And then for H2, we'll take the quadratic term in the expansion of the kinetic energy. It's E squared over twice mc squared times the vector potential A of R quantity squared. Now, it turns out that when you treat these terms in perturbation theory in this order, you find that the contributions of H2 are smaller than H1. In fact, you get an expansion in the fine structure constant in terms of the quantities you're ultimately interested in. We're going to be doing several applications here in the emission and absorption of radiation, and we're only going to calculate them to lowest order. And so that means that we only need to have H1 and we can ignore H2. We can work in first order time-dependent perturbation theory with H1. And in fact, that's what we're going to do. Now, what about the state space upon which this Hamiltonian acts? If I write this as E as the total state space, E total, it's a tensor product of the state space for the matter. And this is the usual Hilbert space we've been using of matter wave functions. A tensor product with the electromagnetic Fock space, which is the one we were just talking about earlier in this lecture. So this is the state space. If we want a basis in this space, the basis in this space is equal to a basis in the matter space. Well, let me denote this as Ketz X like this. I'll use capital letters like X like this to indicate atomic states. So that's what we have for the matter. It's basically the states, atomic states of the single electron Hamiltonian here. And then for the electromagnetic field, we'll use the occupation number basis states, which are specified by a string of occupation numbers in lambda in a manner which has been explained in earlier lectures. All right, so let's let that be the basis. One thing to notice here is that this H0 has the atomic Hamiltonian in the first term and the free electromagnetic field in the second term, and there's no coupling between them. So under H0, what happens is the atom evolves just like atoms always do, at least like they always did as far as we knew up through last semester. And the field evolves just as we talked about in the last several lectures. It's a free field, and there's no interaction between them. However, what the H1 is going to do is induce transitions in which photons are either emitted or absorbed, and that's what we're going to be focusing on. Okay, now we want to use time-dependent perturbation theory for this. So in time-dependent perturbation theory, we have well, before I get started into that, let's take a specific problem. Here's a specific problem let's work on. Let's take a problem of spontaneous emission. So let's do spontaneous emission. Let's set it up this way. Let's have two atomic states. Let me call them A and B. A is the lower state and B is the upper state. And let's suppose that at the initial time, we have an initial state in which the matter is in the upper state B, and the photon field is empty, so we have the vacuum. That's an example of the tensor product of such states like this. This is the initial state. And for the final state, which I'll call N, this would be one in which the atom is in state A, and the photon field has acquired a single photon because there's been an emission of a photon taking us down here like this in some mode lambda. So the photon field has got an A lambda dagger applied to the vacuum like so. It's a tensor product of those two states. Let this be our initial and final states. So this corresponds to a process of emission of a the atom makes a transition to a lower energy state and emits a photon in mode lambda. All right. If I write down the energies of these initial and final states, initial is just equal to E sub B, which is the energy of the atomic state, whereas En, the final energy, is equal to E sub A plus h bar omega, where the omega is the frequency of the photon emitted. Now then, this is some setup then for use of time-dependent perturbation theory. In time-dependent perturbation theory, you may remember the general idea anyway that we had expressions for the amplitude, the transition amplitude, call it Cn of t. This is in first order time-dependent perturbation theory. It's given by 2 over I h bar, a phase e to the I omega ni times t over 2 times this function sine omega ni t over 2 divided by omega ni times the matrix element between the initial and final states of the perturbing Hamiltonian, H1. By the way, the symbol N was used here for the final state because in general, we're interested in more than one final state. So N is a variable final state that we sum over to get physical answers. We'll see in a minute how we do that. But for a specific final state, which means for a specific mode of the outgoing photon, because and also the ground state A for the lower state A for the matter. That's what N refers to here. Okay, now we're obviously going to need this omega ni, and that's by definition is the difference between the final and the initial energies divided by h bar. It's an Einstein frequency, but En and ni we've got up above. This is equal to Ea plus h bar omega minus Eb divided by h bar, and that just turns into omega minus omega Ba, where omega Ba is the Einstein frequency connecting the two atomic states, the upper and the lower, Eb minus Ea divided by h bar. So omega Ba is the frequency we would expect for a photon emitted connecting these two states of the atom. And this omega ni is equal to the actual frequency of the photon minus that frequency. So you can see when omega ni goes to 0, we get energy conservation. That is to say, the energy of the photon is equal to the energy difference in the two atomic states. This is how this always works in time-dependent perturbation theory. The omega ni goes to 0 is equivalent to energy conservation. That's how it happens. All right. Now we're actually going to be more interested in the transition probability. Let me call it Pn of t. If I wanted to make this more a clear notation, instead of n, I could write it as a lambda of t, meaning the atom is now in atomic state A and a photon in mode lambda has been emitted. In any case, the probability of being in that state is just the square of the Cn of t. At least that's what it is in first order time-dependent perturbation theory. And that in turn can be written as 2 pi times t divided by h bar squared times this function capital delta sub t of omega ni times the square of the matrix element connecting the initial and final states, like so. Where this delta sub t of omega has the property that if you take the limit where t goes to infinity, this turns into a Dirac delta function of omega. I'm just reminding you some things that we went through before in the formalism of time-dependent perturbation theory. All right. So we know what omega ni is here. It's omega minus omega Ba here. So that's just replaces by omega minus omega Ba. That's what's going to go into this capital delta function. To work out the rest of this Pn of t, let's turn our attention to the matrix element. Let's take a look at that. So in H1I, what is this? Well, the N is the lower state A, and then it's the state with a photon in mode lambda, but I had to turn it into a broad. See, where is it back up here? Let me show you. Here is the here's the final state. It's A dagger lambda 0. If I turn this into a bra, then what I get is what I've just written down right here. Then we have H1, which is E over MC times P dot A plus S dot B. And then I have the initial state I, which is the atomic state B with nothing in the vacuum, with nothing in the field, that's to say with a vacuum state. So this is what we have. Now this matrix element has both, as you can see, it has both a field part and a matter part. The field part has got the vacuum bra and ket on the two sides, like so. And field operators include the A lambda here, the annihilation operator at that point. But there's also field operators inside A and B. A and B are represented by Fourier series. I showed you them at the beginning of the lecture here. These are Fourier series. The general structure is there's some constants in front. There's a sum on modes lambda. There's a bunch of other constants, and you get a linear combination of A lambdas and A lambda daggers that are in there with a bunch of stuff like that, just to make it schematically what it looks like. That's what both A and B look like, as Fourier series like that. I have to be careful here because the lambda refers to the mode of the emitted photon, and this lambda down here is the dummy index of summation. So let me put a prime on that lambda to make that clear that it's not the same one. Now then, you can see then that that in these two terms here, there's an A and there's an A dagger in this Fourier series. The A terms, the annihilation operators, are adjacent to the vacuum ket. And so they're going to vanish. They're going to annihilate the vacuum and give you 0. As far as the creation operators are concerned, you can see that there's an infinite sum here over all lambdas, lambda primes, but only the term that has lambda prime equal to lambda is going to give you a non-zero answer. That's because if I isolated the field part of this matrix elements, 0, A lambda, there's the A lambda right there, and then an A lambda prime dagger coming from the Fourier series with a 0 on the other side. But this is a Kronecker delta lambda lambda prime. This is a version of our useful identity that I drew your attention to a little earlier, which is now given in box form. This is what it looks like in box form. So what that means is only the lambda equals lambda prime term of this Fourier series survives. And so with that kind of a general overview of how this calculation is going to go, we can write out this matrix element now. Let me first take the E over MC first. So that's a common factor here. Both the Fourier series for A and B have the same prefactor. It's a square root of 2 pi h bar c squared over volume V. I'll put that in next. Inside the Fourier series, if you look at them, there's 1 over the square root of omega is also common for both the series. And now what we need is we're only going to be picking up the one term, which is the creation operator for mode lambda prime equals to lambda. And when the field matrix element has been done, then that Fourier series just turns into a single term, and all that's left is an atomic matrix element. So now what I've got is the atomic state A on the left from here, and then the momentum P is going to get dotted into the complex conjugation of the polarization vector that's coming from the Fourier series for A. And then the spin S comes in with a minus I times spin S, which is dotted into K cross the polarization vector. That's from the Fourier series for the magnetic field, and that's complex conjugated. This is multiplied by e to the minus I k dot r, which is also a term from the Fourier series. And then we've got atomic state B on the right-hand side. So we get to the matrix element we started with is reduced now to a bunch of factors multiplying what you can see is an atomic matrix element, purely atomic matrix element. We'll analyze this atomic matrix element probably in next lecture, but for right now, let me just make an abbreviation for it so we don't have to write it down so often. The abbreviation is this, I'll call it MBA, and I'll put a factor of I over H bar in front of it for really no good reason. And we have state B on the left, and then we have P dotted into epsilon in the middle, plus I times S dotted into K cross epsilon. And then we have the phase factor e to the I k dot r from the expansion of the plane waves. And then we have atomic state A on the right. This is a definition. It's all it is. But let me just point out some things about it. In the first place, if you want to, you can move the e to the I k dot r to the left here, if you want. And the reason is that, well, in the first place, the e to the I k dot r commutes with the spin term because position and spin commute, and the rest of it is just C numbers. The e to the IKR also commutes with the p dot epsilon for the following reason. If you work out the commutator of p vector dotted in epsilon, here's the polarization vector, you see. I'm been leaving off the lambda subscript, but I can put it on. And then you have the e to the ik dot r. It's straightforward to work out that commutator, and it turns into the momentum. Excuse me. It turns into the wave vector k dotted into the p. You see, it gets derivatives. It brings down a k, dotted into epsilon hat, multiplied times e to the ik dot r. But k dot epsilon is 0 because the light waves are transverse. So by transversality, this commutator vanishes, and that explains why I can move this e to the ik dot r to either side I want. Now, with that understanding, you can then see that this matrix element we got for our matrix element that we're interested in here for the spontaneous emission of photons, this thing right here, this can be written as IH bar times MBA complex conjugated. And so let me go to a new page and summarize that result. The result is this, is that NH1I is equal to E over MC square root of 2 pi H bar C squared over volume V, 1 over the square root of omega times IH bar times MBA complex conjugated. By the way, before I leave this MBA definition behind here, let's go back and look at it a bit. This MBA definition, let's look at it. The question is, what does it depend on? Well, it depends on B and A, certainly, because those are the two atomic states on the two sides, and that's what are indicated here by the subscript. It doesn't depend on momentum or spin because those are, or position vector R, because those are operators for the atom, and once you take the matrix element, they disappear. But the polarization vector epsilon and the wave vector k are just C numbers, and so they survive, and so the MBA depends on those. What we can say is that MBA depends on the two atomic states and on the mode of the outgoing photon. That's what it depends on. So let's keep that in mind. In any case, then, this is our matrix element, H1, this matrix element. This now means that the probability to find yourself in state N, which, as I said before, is a state A lambda of T, labeling in a different way, to write it out in all detail, is going to be 2 pi T over H bar squared times capital delta sub T of omega minus omega BA multiplied times the square of the matrix element, which is E squared over M squared C squared, 2 pi H bar C squared over volume V, 1 over omega, I'm just running through this and squaring it, H bar squared, the absolute value of MBA, which depends, as I say, on K vector and epsilon hat, quantity squared. All right. All right. So that's the transition probability to a single final state. This is getting somewhat dark, and I'm wondering if I can clear this up if I make it look better. Somebody should complain about this so that I can. All right. I hope that's an improvement. Hope that's an improvement. All right. Good. Now. All right. Now. As usual in problems like this, we're not so much interested in transitions to a single final state, to a single mode of an outgoing photon, but rather we want to sum over final states. The way I set this problem up, the lower atomic state A is fixed. It's just the state we're making a transition to, but what's not fixed is the mode of the outgoing photon. So let's talk about that a little bit. Let's set up a diagram to show what states we want to sum over. It's just a coordinate system X, Y, and Z. And let's say we put our atom at the origin of the coordinates. let's choose an outgoing direction I'll call in hat sub f, where f just means final, in hat final. We choose that. That's the direction in which our measurement apparatus is counting, our photomultiplier tube is out there counting photons. And let's construct a small cone of solid angle delta omega around that. This is similar to what we did in scattering theory, as you'll recall. So the kind of quantity we're ultimately going to be interested in is what I'll call dw d omega. Now, I'm sorry, a w is not the same as lowercase omega. This is a w, and this is omega, which is the Greek letter. And I try to keep them pretty distinct as best I can, but I notice some students have a hard time drawing the difference between them. So I hope this won't make it trouble for you. In any case, as I've done before, I'll use the symbol W to stand for a transition rate. So this has dimensions of inverse time or probability per unit time or number of particles per unit time, whatever. Here in the present case, it's going to be probability per unit time. And what we want is the probability per unit time per unit solid angle for the photon to go out inside this cone. And so what that's going to be is it's going to be the total probability divided by the time. So it's 1 over t, and it's per solid angle. So I have to divide by 1 over delta omega. And then what we need to do is to sum over photon states in which the k vector is inside the cone. And then what we sum is the p a lambda of t. This is the quantity that we want. We need to work this out. So let's do that. All right. Now, the way to do that is to first take a look at this k over the cone. K over the cone, when we let the volume of the box get large, becomes the density of states in k space, which is the volume over 2 pi cubed times the integral d cubed k over the cone. We transfer from a sum over to the integral. That integral, in turn, since the angular integral is only over the small cone, that just becomes equal to delta omega for the angular part of the integral times an integral from 0 to infinity of k squared dk, the radial part of this three-dimensional k integral. As far as that radial part is concerned, it's convenient to transform that to momentum as a variable of integration, to frequency as a variable of integration. So it becomes 1 over c cubed times integral 0 to infinity of omega squared d omega. All right. So we want to put all this together along with this formula up here for Pn of t that's strung out like that. And so allow me to do that. Well, if I do that, let's do some cancellations here. The 1 over t here will cancel with the t, which is up here in the probability. Probability grows in proportion to time. We divide by time in order to get a rate. The delta omega, which is here, is going to cancel with the delta omega there because we got per solid angle. That ought to cancel too. Something else that should cancel is the volume factors, and they do. The one from the density of states cancels with a v here that was a prefactor in our Fourier series. There's some other cancellations too. There's a h bar squared there and an h bar squared there that go away. There's a 2 pi there and 2 pi there, which kills 2 out of the 3 2 pi's there. There's a speed of light squared here as it cancels somewhere. Yeah, here, c squared there cancels with the c squared down there. Okay, so all of that. This delta function, let's replace this by a Dirac delta function of omega minus omega BA. And I'll come back to that later to tell you about what justifies that. This is only valid in a long time limit, but we need to worry about how long a time is required for that substitution to be legitimate. And I will come back to that question in a moment. But if we do all of that, then what we get is a formula for dw d omega. Let me put all the pieces together here. So running down here, I get all the prefactors. I get over 2 pi. I get over 2 pi c cubed coming from all these prefactors. And then there's an e squared over m squared there, e squared over m squared. Let me put that in. And then what we get is the integral from 0 to infinity of let's see, this omega in the denominator there is going to cancel with one of the omegas there. So I get integral 0 to infinity of omega d omega. I then have the delta function, delta of omega minus omega BA. And then there's a factor of h bar, which I omitted here. There's an h bar, I'll take that out. And then there's just MBA squared, which depends on, as I say, k and epsilon hat. Okay. Now, the k here is a vector, but the k vector has to lie inside the cone. So it's equal to the magnitude of k times the n hat final. That's where n hat final comes in. It fixes that value of that k vector there. The integral, of course, has a delta function in it, and that fixes the value of omega. Omega then also fixes the value of k, because k is the same thing as omega divided by c. So doing the radial integral, you see here, now in terms of the variable omega, is going to fix the value of omega at omega BA, which is the energy, is the Einstein frequency between the two atomic states. And it's going to fix the magnitude of k, what appears in MBA according to energy conservation, where the direction of k is in the outgoing direction of n final. This n final you can think of as being specified by angles theta and phi, and that's what's implied here in this omega in the dWd omega here for the transition rate. Okay, so if we do this integral then, which is easy to do because of the delta function, what we get is we get dWd omega is equal to e squared over 2 pi m squared c cubed, I'll write it that way, times h bar omega times the absolute value of MBA of k vector and epsilon omega, epsilon mu squared. All right, and let me box that, because this is a major result of this calculation. This is giving us the differential transition rate. By the way, the right-hand side still depends on the polarization of the photon. So let me put a subscript here in this dWd omega. This is the differential transition rate, probability per unit time per unit solid angle when the polarization of the outgoing photon is mu, and it's given by this formula here. So this is giving us quite a lot of detailed information about the photons that are emitted by the atom. It tells us in the different directions. Basically resolves the transition rate, not only by direction, but also by polarization of the outgoing photon. And here's an explicit formula for this. This formula is quite easy to derive by quantum electrodynamics. We just did it. It's the formula is just a matter of chasing through all the factors and getting the factors of 2 correct. And otherwise, it's a straightforward application of time-dependent perturbation theory, first order. You may, in your undergraduate courses, have derived a formula like this. Probably not this. You probably derived the total transition rate, not resolved like this. But even getting the total transition rate, if you use what's called the semi-classical theory of radiation, it's a really complicated derivation, and its only virtue is that you can do it without knowing how to quantize the field. So once you've gone through the labor of doing that, then deriving this is actually quite easy. And as you can tell, it's got quite a lot of data in it, quite a lot of detailed information in it. Now, given this result, an obvious thing to do is to sum this over polarization and integrate over solid angles to get the total rate of spontaneous emission. Let me just call that W. That's equal to the integral d omega, a sum on polarizations mu, of dW d omega of mu, like so. And so the thing that depends on the solid angle omega, or the direction of the outgoing photon and in its polarization, the only thing on the right-hand side that depends on that is this matrix element here. Allow me to make a definition. I want to define an average matrix element, MBA squared with an overbar, which means an average. And this is defined this way. It's 1 over 4 pi times the integral d omega times 1/2 the sum on mu of MBA absolute value squared, which is not averaged, which is what we have here. Averaging eliminates the dependence of the matrix element on the polarization, and it also eliminates the its dependence on the direction of k. That's what the omega refers to here. So the result is that this final MBA is a function only of the magnitude of k, or equivalently a function of omega. It depends depends only on omega. Let's just say depends on only on omega. All right. Okay, and if we do this, then we can write down the total transition rate W like this, and just running through this formula, we need to multiply by 8 pi to put a bar over the m. And so what we get is 4e squared divided by m squared c cubed. And then we have MBA, absolute value squared, averaged over polarizations and angles. And this then is the total transition rate from atomic state B, the upper state, to the lower state A. This is also denoted as this is also called the Einstein A coefficient. The E below here means Einstein. This is the Einstein A coefficient. The Einstein A coefficient, by definition, is the total rate of transition for spontaneous emission between the upper state and the lower state. And now we have an explicit formula for it.
What happened to the h bar omega?
It should have been there. Your eyes are really good. Thank you very much. That h bar omega should be there. Yes. Okay. Anyway, that's the formula for it. I have a summary sheet here where I'm kind of collecting these results because the intermediate steps are complicated enough that it's worthwhile doing that. And let me flash it at you at least. Here's the summary sheet. So what I've got here is a useful abbreviation, this matrix element MBA here. We'll have to worry about evaluating that later. But for spontaneous emission, we obtain the differential transition rate, which is given by this formula. And then we get the total transition rate, which is the Einstein A coefficient here, where the averaging is defined down there. I think these are the principal results for spontaneous emission. Now, are there any questions about that before I go on? If not, I will proceed. Next, we want to turn our attention to absorption of radiation. It's kind of the reverse process. So let me get the summary page out of here. Let's now talk about absorption of radiation. So in absorption, we're going to have two states again. Let's again call the upper one B and the lower one A. But the difference now is that A is going to be the initial state, and it will absorb a photon, h bar omega sub lambda, from some mode lambda from the field and get lifted into atomic state B. Now, so the initial state then is a state in which the matter is in state A, and the field is something else. Now, you can't absorb a photon from the field unless there's some photons in the field. So the initial state A has to have some photons in it. So to set up a simple model, let's suppose that the state of the field is an occupation number eigenbasis state, specified by a string of integers, occupation numbers in sub lambda like that. And let's suppose that the lambda that I've written here refers to the mode from which the photon is absorbed. If that's true, then the final state, which I'll call n here, is the upper state B, multiplied by a field state vector, which is n lambda minus 1 in the lambda slot. The meaning of this notation here is that these two occupation number basis states have all the same occupation numbers in all the modes, except for the one mode lambda from which the photon was absorbed. And in that one, the occupation number went down by 1, which is kind of obvious from absorbing a single photon. In any case, let's let that be our initial and final states. Now, the rest of this is a slight variation on what we just did. We need to go through first order time-dependent perturbation theory. So let's get omega sub ni, which is equal to En minus Ei over h bar. And this is going to be when all the modes that haven't changed, they cancel out when you subtract En minus Ei. What's left over is that you're going to get an Eb, E sub B minus h bar omega minus E sub A over h bar, which is equal to omega BA minus omega. Omega is the frequency of the photon that was absorbed. This omega BA minus omega is the same omega Ni we had before in the case of spontaneous emission, except for the opposite sign. That's the only thing that's changed with this. All right, in any case, that's the omega Na. Now, what about the matrix elements in H1I like this? the final state in, to write it out as a bra, now is going to be a B here. We've got in photon modes with one less photon in mode lambda. That's the N is bra. H1 is E over MC times P dot A plus S dot B as before. And then we get atomic state A, and then we get a state of the field with lots of photons in lambda like that. All right, now again, the A and B are Fourier series. I'll write as a sum on lambda prime, indicating it schematically. There's an A lambda prime, and then there's an A lambda prime dagger. And there's some coefficients out front. You'll recall that in the case of spontaneous emission, we only had the creation operator. The annihilation operators didn't contribute. For the case of absorption, it's the opposite. Now it's the creation operator which contributes, and the annihilation operators don't. Here's why. The initial state of the electromagnetic field has certain numbers of photons in all the modes. The final state has the same numbers of photons in all the modes except for mode lambda, where it's gone down by 1. Therefore, to go from the initial photon state to the final photon state, you must annihilate a photon in mode lambda. What that means is the creation operators don't contribute. And in fact, the only annihilation operator which does contribute is going to be one for which lambda prime equals lambda. Again, this sum on lambda prime reduces to a single term. In fact, the matrix element that we have for the field is this. It's in lambda minus 1 like this as a bra. Then we've got an A lambda, the annihilation operator. And then we've got in lambda like this on the right-hand side. Now, A lambda acts on this part of this here is the same thing as the square root of n lambda times n lambda minus 1 in the middle, like this. We get this is just using harmonic oscillator formalism, which I think you all know. We get a square root of n lambda coming out, and then this state that's left over and the bra on the other side are just cancel each other out. They're by the normalization. So the result is just we get a square root of n lambda that appears here. This is something that's different from what we had in the case of spontaneous emission. All right, and if we do this, then put the matrix element together more clearly, then we have in H1I is going to be E over MC from the common factor in front of the H1, the square root of 2 pi H bar C squared over volume V, which is a common factor in the two Fourier series. We get 1 over the square root of omega, which is also a common factor inside the two Fourier series for A and B, but we get a square root of n lambda on top. This is omega lambda and n lambda like that. And then what's left over is a purely atomic matrix element. I'll write it out here. It's going to be B on the left. It's going to be the momentum P dotted into the polarization vector epsilon plus I times the spin dotted into K cross epsilon. That's multiplied times e to the I K dot R. And then we have atomic state A on the right. And this, lo and behold, is our MBA all over again. It's multiplied times minus IH bar MBA. This time it's not conjugated, complex conjugated. And then this gives us then an expression for, I'll write it out, in H1I is equal to E over MC square root of 2 pi H bar C squared over volume V, square root of n lambda over omega lambda, square root of omega lambda, times minus IH bar times MBA. So this is for the process of absorption. Now this matrix element is almost the same as what we had for spontaneous emission. The only difference is that number one, it's been complex conjugated, and number two, there's a square root of n lambda there. The square root of n lambda, when we go to the transition rate, we have to square the matrix element, so that becomes proportional to n lambda itself. This has the physical meaning that you see it's going to enhance the rate of absorption depending on the number of photons that are in mode lambda. in other words, the absorption rate is proportional to the number of photons that are in the mode. And because there may be many of those, it enhances it possibly can enhance the absorption rate much above what you had for the rate of spontaneous emission, where there was no such square root. This has a simple classical interpretation, which is that if you have an oscillator, a harmonic oscillator, and you drive it with a wave, the harder you drive it, the more transitions you get to excited states. All right. Anyway, that's the meaning of that. Let me consult my notes here. I'm running out of time, so let me consult my notes here and see if I can abbreviate some of this a little bit. Let me just say that if you put all this together to compute the absorption rate, we won't try to resolve the absorption rate by angles as we did for spontaneous emission, because it doesn't make that much sense. You're absorbing photons out of a given field. But in any case, the absorption, so we just sum over all possible final states, all possible modes of absorption. And if you do, you get this. You get E squared over 2 pi m squared c cubed h bar omega integral d omega sum on polarizations mu. You get the n lambda, which is, I'll remind you, is the number of photons in mode lambda in the initial state before the atom got lifted into its excited state, multiplied onto MBA, which depends on K and epsilon sub mu, absolute values squared. Okay. All right. So this comes out, the details I'm skipping are chasing around all the factors of 2 pi and c squared and h bar and so on. If you do all that, this is what you get. Now, this was all calculated assuming that in the initial state, we had an occupation number eigenstate of the electromagnetic field in which we knew all the numbers of photons in all the different modes. As a practical matter, it's very unlikely that you'll ever have that. You won't know how many photons are in each mode. There's, for one thing, there's an uncountable, there's a large number of modes, right? It's much more likely that you have only statistical information about the numbers of photons in a mode. For example, in the special case of black body radiation, the average number of photons in mode lambda is given by the Planck formula. It's 1 over e to the beta h bar omega minus 1. So now, I don't want to assume that this radiation is black body radiation, but if it were, we have a nice simple formula for the n lambda. In any case, let's assume we know what the average value of n lambda is. Then it's appropriate to take this expression and replace the actual n lambda here by its average value, because that's probably what we know. You can formalize this by creating a density matrix for the electromagnetic field in the initial state, and using the average values of n lambda to create that matrix, and then taking traces over that and all that stuff. But it amounts to just replacing the n lambda there by its average value. All right. Now then, supposing we've done that, the lambda here, of course, means k mu, so it's the mode of the photon, including its direction and its polarization. The magnitude of k is determined by energy conservation. That's the energy that it took to lift the atom into the excited state. But the direction of k is arbitrary. And you see we're integrating over that solid angle there and summing over polarization. So the polarization is arbitrary too. It includes all of those. So this n lambda then depends in general on the direction of k and on the polarization, as does the matrix element. And so there's nothing I can do with this averaging, this integral and this sum here. I can't turn it into an average over MBA because the n also depends on the variables in question. On the other hand, if the radiation is isotropic and unpolarized, which, by the way, black body radiation would be isotropic and unpolarized, but I don't want to assume that. I just want to assume it's isotropic and unpolarized. Then this means that the n lambda, or the average n lambda, is independent of the direction of K and also independent of the polarization. Therefore, the only thing that's left for it to depend on is the magnitude of K, which is effectively saying that it depends on omega, because omega equals CK. And if that's the case, if this becomes equal to average value of n lambda, which is a function of omega, then it can be taken out of the sum here. And what's left is you get the integral in the sum of MBA, which can be expressed in terms of the MBA squared. And if you do this, then what you get is you get W absorption is equal to, I won't write out all the detailed formula because most of it turns out to be the same as the Einstein A coefficient. It turns into Einstein A coefficient. It's the same calculation, now multiplied times the average value of n lambda as a function of omega. So the rate of absorption then, with isotropic and unpolarized radiation between the two atomic states, is the same thing as the rate of spontaneous emission from the upper state to the lower state, multiplied by the average number of photons in the mode in the initial state, like this. Okay, it's a connection between now emission and absorption. Now, I've got about, looks to me like about 45 seconds left before the clock rings. I didn't get as far as I wanted to, I never do. We'll pick up with this next time, but this leads by a short argument to a relationship between the Einstein A and B coefficients, which played an important role in the history of quantum mechanics. And the whole story of the Einstein A and B coefficients and the general arguments surrounding it are still important in applications, even today, although the original purpose that Einstein put this argument to was quite different. In fact, let me do this. Let me terminate the actual lecture and ask if there's any questions what we've done so far, and then anybody wants to stick around, I'll tell you a little bit about what Einstein's original argument was. So are there any questions about what I've done so far here? All right, well, if not, then I'll tell you what Einstein was doing with this. He wrote a paper in 1917 or 1918, I'm not sure what it was. It's where the A and B coefficients first appeared. He was trying to do, or he did it correctly. He was doing something that Planck had tried to do for a long time during the 1890s, which was to develop a detailed kinetic theory of how matter interchanges energy with the radiation field when it's in thermal equilibrium with it. And Planck set up models of harmonic oscillators and emission and absorption of radiation using classical electromagnetism is how he did it. And he invested a lot of effort into those kinds of models. Einstein returned to that in 1918 because he was interested still in understanding the Planck formula. At that point, nobody yet really understood the Planck formula. And so he again set up this kinetic model. But in Einstein's model, he had an atomic system, now a matter system, that had two discrete levels, the A and the B. I'm calling them A and B. That's not the same as his A and B coefficients. That's the name of the levels. But he had a two-level system, which is a simple model. But the point is there were quantized levels, which Planck didn't know about when he was doing it. And he set up a kinetic theory for the rate at which transitions were made between the levels in the process of emitting and absorbing radiation. And he made some critical assumptions in there. One of them was that the rate he made one assumption he made was that the rate of absorption, which is this W, he made the rate of absorption, he said was proportional to du d omega, which is the energy density in the field at the given frequency, with a proportionality constant that he called B sub E. That's the Einstein B coefficient. And the second assumption he made was that there was a non-trivial rate for spontaneous emission on top of induced emission. And he put these pieces together and was able to derive from that the Planck formula for the black body radiation and thermal equilibrium. In other words, he did what Planck had not been able to do, or Planck had only done in a. It's really fair to say that he did what Planck had not been able to do. So that was the original purpose to which the argument was put. Nowadays, the argument tends to be used in introductory courses in quantum mechanics to derive the rate of spontaneous emission, because once you've got the connection between the two, then you can use the semi-classical theory of radiation to compute the B, and then Einstein's relation from that to get the A, and that gives you the rate of spontaneous emission. Anyway, that's the story on that. Okay, so are there any other questions then before we quit?
I was wondering if there was some sort of like time reversal argument to get the second result if we already had the first one, or maybe I guess vice versa would be the better, easier way to do it. But something like that. In the case of at least isotropic unpolarized, because atoms don't preferentially emit, at least as far as I know.
Atoms don't do what?
I was just saying, I guess we kind of assumed that the spontaneous emission was isotropic and unpolarized.
Oh, no, it's not isotropic. In fact, that's the whole point of this formula, is it gives you the angular dependence here. Right up here, you see. It's giving you the angular, oops, sorry, I'm not screen sharing anymore. No, but go back, you'll see the formula for the differential transition rate explicitly has an angular dependence in it. It gives you all of that. For
Sorry, I meant the
spontaneous.
total though. Never mind. Yeah, I guess I was wondering if there's like a time reversal argument to connect these two. Or something.
Yeah, so what they call detailed balance doesn't depend on time reversal. It has to do with thermal equilibrium, you see. That's a different issue. But I think I'm not prepared to talk about that in detail.
Okay.
But what Einstein assumed was detailed balance, and that means there's as many transitions going one way as the other, and that's necessary for thermal equilibrium.
Okay, cool. Thank you.
All right. Any other questions? All right. If not, thank you for your attention, and I will see you in 2 days.